if you've got questions. I'm really hoping that all of this actually showed up and that was just not a lag in my camera. That's a bad sign. So it's looking like it cut off the first like 10 minutes of this. So let me go back over this one more time just in case. So I got asked a question about how do you do the POH from KB problems. And let me start over. Just in case it really did cut off the first 10 minutes of this video because of a weird lag issue. So to do these types of problems, you're going to solve them the same way you solved any equilibrium problem. You need the expression for Q. So Q here is concentration of OH minus, concentration of biphosphate, and concentration of phosphate. We have Q equals KQ in this case, KQ is KB, and we need our IC table. Now what we're being asked to solve here is POH, and P here is a mathematical operation. So P is the negative base 10 log of the concentration of OH minus. So what we need to find the POH is the concentration of the OH minus at equilibrium. Now this is a diagnostic problem, meaning that it's meant to be easy math. So it's 0.1 for the starting concentration of phosphate, 0 for the other two, it's X, and X. So we get 0.1 minus X, and X. So we're going to stick this E row here in for concentration. So we get X times X all over 0.1 minus X. And when we solve for X, thank goodness I didn't close this out, you get 0.02521518. So to find the POH, because X here is going to equal the concentration of hydroxide, we're just going to take the negative log of that number, and we're going to end up getting 1.7. Now, the reason I'm going to stick to 1 decimal point for the answer, usually if there's like slight errors with how your calculator solves it, like just machine errors, you're going to find that that 1 decimal point kind of absorbs a lot of that. But yeah, there's no rules for sig figs here, so just do whatever the problem says. Now, what I find confuses students is they conceptually don't understand what pH and POH are. pH is just the negative log of the concentration of H plus. POH is the negative log of concentration of OH minus, and they have to add up to be 14 for water. And there is a proof for this in the notes, but you get this conversion factor that pH equals 14 minus POH. And so if we want to know the pH of this solution, the pH here is just 14 minus 1.7 or 12.3. So you're probably familiar with the pH scale. This is something you would have worked with like in high school. Low pHs are acidic, high pHs are basic. So a low pH, less than 7 means acidic, but this is a base. And the thing is that, because I did start out the video by saying this, assuming you didn't cut it off, we're pretty much going to be working exclusively with Bronsted bases when it comes to weak acid-base chemistry, not Arrhenius bases. So in Arrhenius base, the base contains the hydroxide and lets go of it. In this case, this is going to be a proton acceptor. The reason why we're going to work with the Bronsted definition, there are no weak base Arrhenius bases, so we have to work with the Bronsted definition. And you are expected to know this for the next exam. If I say you're working with a base and I just give you the compound, the base is going to accept a hydrogen, and you have to be able to write the reaction out based on that. So even though we have a low POH, the pH here is really 12.3. So POH and pH are not the same thing. They represent different quantities. This is the concentration of hydroxide. This is the concentration of H+. H+ is the acidic component of water. OH- is the basic part of water. Other big things. This part here is pretty much easy compared to the last exam. What we introduced with test 4 are what are called the periphery problems. So pH and POH, this is a calculation that's done on the back end. After you go through the trouble of finding the hydroxide or the H plus concentration, then you convert to pH and POH. Up here, we're going to have periphery problems like dilution. So M1V1 equals M2V2, or N over V equals M. So how much acid would you have to dissolve to get a certain pH? But these periphery ideas aren't really part of this table so much as they're a part of trying to figure out aspects of this table. So this is kind of the difference between the previous problems you did for the last test and what you're going to be doing for this test, is that instead of just solving for numbers in the IC table, you're going to have to go back through now and actually start calculating things with the numbers you find. This introduces chances for error, but these are also much more simplified problems relative to the ones that you started with when you were doing the last exam. So for example, the next question on here says, okay, now at 0.1 for the cellular concentration of the biphosphate, it's still the exact same setup, and you're still going to go through here and find the pH after you find the POH. And then you also have a homework set where it tells you to ask you to find pH in the POH from the KB. It's all of this. You just add this last step onto the end of it to find the pH. But generally speaking, what students find with this set of material is that it's actually easier than the test 3, because one, the test 3 had all the Hess's law stuff on it, and 2, the equilibrium problems could be a lot more complicated. With acid-base chemistry, it's pretty much the same problem being solved every time. You're just kind of changing what's in the IC table. In fact, during normal semester, I just write this really big, take an eraser to all the individual squares because nothing really changes. All right, so that's all I had for questions that were asked in advance. I've got the chat menu open, so I'm going to leave it up for about 4 more cameras on for about another 4 minutes. If you got questions, please feel free to ask them. After that, I'm going to get a little bit of work done, but I am going to be here visible in the chat. right, no questions. I'm just going to turn the camera off. Again, I'm still here. I'm just trying to get some work done. I don't really think you want to listen to me type. All right, so we got a question. Can I do pH from P8 from Ka and pKa? First problem. All right, so let me bring up the homework. So is the pH of 0.15 molar solution of monoprobic HiO3 if the pK is 1.23? All right. So we've got our acid HiO3. It's going to do what acids do. It's going to go up a hydrogen, give us H plus and IO3 minus 1 iodate. And we're given a 0.15 molar solution, so we're asked to find it. And here we got the pKa is 1.23. So you got your expression for Q, H plus, iodate, all over hydroiodic acid. And this is going to be equal to the Ka, not the pKa. pKa is a mathematical operation. So the pKa here is the negative log of the Ka. So let's set up our IC table. We're given a starting concentration of 0.150. And you're asked to find the pH, which is the negative log of the concentration of H plus. So we need to find this square in the table. So what we'll do is we'll plug in for our values of Q, our values of all these. So we got x times x, 0.15 minus x. And when you rearrange this, you'll get that x squared plus Kax minus 0.15 times Ka equals 0. Now, I would recommend solving this symbolically first and then actually start plugging in. So if you use the quadratic equation, you'll get Ka is just 10 to the negative pKa. So if we undo this, Ka equals 10 to the negative pKa. So Ka in this case is 5.89 times 10 to the negative 2. So if I stick all that in there, 0.15, I'll get that x in this case is 0.069044. And when I take the negative log of that number, I get the pH is 1.2. Yeah, I'm guessing the confusion here is, and I've definitely seen students doing, is they stick pKa in equals Ka. They're not. This is a mathematical operation. Ka does not equal the negative log of Ka. There's no such thing. So you've got negative log of Ka equals pKa. So to undo it, we take the negative of both sides. And then we raise 10 to the power of both sides, and that will get rid of the log. And so we get Ka equals the negative log of pKa. And this is the same thing about how you undo pH. To undo pH, the concentration of H plus is 10 to the negative pH. Then to do pOH, the OH minus is 10 to the negative pOH. And again, there's a flow diagram, there's a Blair diagram under the lessons ribbon. It will actually show you a flow diagram about how to go from one value to another. Because if you're given Ka, you can find pKa, pKb, and Kb. They're all found the same way as pH, pOH, H plus, and OH minus are all found. So I'm going to blink the camera back out. But again, if you got questions, feel free to ask them up in the chat. I am actually here. Of course, just to turn the video on. All right, so titration curves. Pretty straightforward. And here we're only going to focus on monoprotic weak acid titrations. We're not going to focus on weak base, and we're not going to focus on diprotic, triprotic. You can do them. They're all kind of the same idea, but especially with weak base, it gets really complicated how you convert Henderson-Hasselbalch to basic conditions. But with your titration curve, you've got a few regions. So we've got the equivalence point, which was on your discussion board. We've got the midpoint, and then we've got the buffer region. So the buffer region exists, so we're going to put the V, EQ here is the volume of the equivalence point, V here at the midpoint, and this axis here is the volume of base being added. So everything above this is base controlled. Basically, you're adding a strong base, and you've exceeded what the buffer can actually, you've exceeded what the weak acid can handle, so now it's all being controlled by the excess strong base. Beneath that, we have the buffer region, and a buffer by definition is a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. We have to have both present. So at 0, and at the equivalence point, we do not have a buffer. It is only between these two regions can we claim that we have buffer or buffer behavior. Now, buffers are unique in a few regards. So if you just take a strong acid and titrate it with a strong base, you don't get this type of curve. You actually end up getting a curve that looks more like this. That happens because your weak acid or your strong acid doesn't resist pH changes in the same way that a weak base does. A weak base sees weak changes, small changes in pH as a function of the conjugate base, or you see smaller changes in pH, particularly around the midpoint. So basically, it resists pH changes better around the midpoint, and we see our best buffering at the midpoint. Our midpoint is half the volume of the equivalence point. And so if we know what the equivalence point is, we know where the midpoint is. So there's a few special relationships here. First, because of the Henderson-Hasselbalch equation, which says that pH equals pKa plus the log of the conjugate base over the parent acid, their concentrations. At the midpoint, which is where we're going to have equal amounts of both, the pH equals the pKa. And this is a consequence of Henderson-Hasselbalch. Now, does Henderson-Hasselbalch have limitations? Yes. There is a big assumption built into Henderson-Hasselbalch, specifically that X, your extended reaction, it's much, much less than the concentration of the parent acid and the conjugate base. Now, you typically don't see these assumptions brought up because typically we are working with greater than 0.1 molar, but if you look at stock buffer solutions, they're 0.1 molar for a reason. If you go to like 0.01 molar, the Henderson-Hasselbalch equation will actually begin to fail because the extended reaction is comparable. So here we're assuming that their starting concentrations, what we add to the solutions, are equal to the equilibrium concentrations. But you know that some weak acid is going to dissociate and some conjugate base is going to absorb some hydrogen. So it's not really true, but definitely if you're above 0.1 molar for both, you're going to be fine. The extended reaction is not going to mess with you that much. But at the midpoint, pH equals pKa. At the equivalence point, assuming that it's 1-to-1 acid to base. Well, actually, let's not even make that assumption. Well, actually, we can't. Okay, so at the equivalence point, the molarity of the acid times the volume of the acid equals the molarity of the base times the volume base, assuming the acid and the base are 1-to-1 and you're working with a monoprotic acid. Now, there is a larger equation that this simplifies from. and it's this equation here. So the molarity of the acid times the volume of acid divided by its reaction coefficient equals the molarity of the base times the volume of the base divided by its reaction coefficient. So if we're looking at acetic acid, I got it written down here, HC2H3O2 reacting with NaOH, going to acetate, C2H3O2 minus 1, plus water, plus Na. Let's do that. Just adding the hydroxide. In this case, these are both coefficients are both 1. But let's say you're working with something like calcium hydroxide. You need to put a 2 down here. So this is kind of like a very special case that we're working with here. Just don't get into that bad habit of assuming it's always this. But particularly for what we're working with, we're going to assume that we're adding something like sodium hydroxide, which is a monobasic base, and we're working with a monoprotic acid. In that case, at the equivalence point, the molarity of the acid times the volume of acid equals the molarity of the base times the volume of the base. And the volume of the base here is the volume at the equivalence point. So this is how you use titration curves to figure out the pKa as well as the concentration of the acid, because you know the volume of acid you added to the titration flask if you were doing in this lab. You know the volume of the base because you know the equivalence point. You know the concentration of the base because that's your standard, that's what you're working with. This is generally the unknown that you're solving for. Now, in practice, how do we find the equivalence point? It's actually not that easy. Generally, what we like to do is actually find the midpoint, because at the midpoint, the second derivative here is 0. And so we can mathematically find it pretty easily on a graph, especially if we go slow with the titrations. The other is that this is also an inflection point here, but it's an infinite inflection point. So here, the second derivative of pH with respect to volume ends up going to infinity. So we basically look for the steepest part of the graph, and from there we can tweeze out where the equivalence point is. But yeah, if you look at all those analyzing titration curve homeworks, they're all solved the exact same way. You know the volume of the equivalence point, the midpoint's half that volume. That volume at the midpoint really doesn't matter, but what does matter is that the pH and the pH at that midpoint equals the pKa. For the equivalence point, that's going to be what you plug in for your volume of base. You're given the molarity of base and the volume of acid, and that will allow you to tweeze out what the molarity of the acid is. Yeah, you're welcome. All right, no concurrent viewers, so we're just going to turn the camera off. And yeah, I am here if you got questions. All right, really not seeing much else going on in terms of the chat activity. So again, these are office hours. These are not lessons. If you have questions, please feel free to send them out in advance, and I will see you all tomorrow.